YouTube is going live. Okay, great. Hello there, everybody. Today we're going to be finishing this schematic and just reviewing the components and just like figuring out what faults we can find. And I know for sure that there are a few issues with the footprints, but I'm going to be going over each component by itself and just making sure that it's in the right place, that it fulfills its function, and that it has the right footprint, the right value, etc. So let's get down to it. Let's see here. Let's go to the components. So I'm just going to do like this. I'm going to just drag this one out here. Let's see, this one is going to go to screen number 5. We can do like this. Screen number 5. Okay. So one thing I noticed also is that I've been using 100 nanofarad capacitors, where like on the same schematic where I also use 50 volt capacitors, 100 nanofarads. And the thing is, I need to have 50 volt capacitors because I have a 24 volt power supply, and I'm using some of them on the input, like on the 24 volt input. So and they are also cheaper. So this means that I can just replace all of the capacitors that are 16 volt with a 50 volt and just reduce the BOM cost that way, because I can just use one component instead of two different components, which kind of makes sense. Like if you look at this, if you look at the 16 volt capacitor, it costs 0.18 euro, which is actually too much for a capacitor. I don't know why. I don't know why I picked that capacitor. But the 50 volt one costs 0.09 euro, which is more reasonable. So it's half the price, which is good. So let's just go over all of the capacitors here. We're going to start with this list. We're going to start from the beginning and just go down the list and just make sure that all of the components kind of fulfill their function. But we'll start with the capacitors here. So we're gonna go. I did C1 and C2. I'm going to go to C3 here. So let's see. C3 is over there. We can just replace this one. And this is the biggest benefit of having all of the parts in a part library. I can just do like this. And I can basically, when I replace all the parts, I can just go like this, update fields. And I should have, actually I didn't click the value, but yeah, we could actually do that. So let's go to the update fields and just click the value there. And then we should have 50 volt. So all the fields are updated to the fields of the 50 volt capacitor, which is great. You know, you should never go the typical route of setting the part numbers or like picking footprints in KiCad, because it's completely retarded. KiCad has this completely retarded workflow where you first place the parts and then you go to this stupid table and just, you know, assign footprints, I guess, or whatever, which is very error prone and not very efficient. So what I do instead is I have a library of parts where I have where I just have my parts. Actually, let's make this window sticky, so we can do like this: i3 message sticky enable, and this window should be sticky. So if I go to let's see. If I go to, yeah, no, it's sticky. That's good. That's perfect. Okay, so I have this library of parts, and I can, when I have the library of parts, I can actually update all the fields automatically using the Python script. And I can just sort of have a bunch of parts that I just reuse. And this makes it easy for me, for example, to change the voltage of a capacitor. So let's go to the next capacitor. We have C4. Let's go to C4. C4 is 10 picofarads. I suppose it wasn't C4 then. Which one was it then? It's actually 1, 2, 3, C8. C8 is the next one. C8. Let's see where C8 is. C8 is over there. We're going to replace all of these ones with the 50 volt part. And See how it updates right away on the in terms of the symbol. And I've never actually seen anybody do it this way, which is why I do it. Which is actually not exactly why I do it. I do it because it's very practical. I do it because it's very practical. Fucking cough. And the cough doesn't get better when I'm eating these nuts. But I eat them anyway because they taste good. Okay, so we got 8, 9, 10, 11, 12. Let's have a look here. Okay, so we have 8, 9, 10, 11, 12. We have 13 and 14. Let's make this one 50 volts. And 14. And 14 is over here. So it's going to be 50 volts as well. Sounds sacry. What the fuck is sacry? Scary, I guess you meant to write. Let's see what sound we can get. Today I felt like listening to country music. Sometimes I like to listen to country music. Let's see, C4. C4 is a 10 picofarad capacitor, 50 volts. And I think for the 100 nanofarads, I've actually checked this part, so I know this is. Let's actually double check this, because you never know. I should actually find some way to mark the parts that I've checked them, which is next on my to-do list. So once I'm completely 100% sure that a part is correct, I should actually mark it in my library so that I don't have to check it again. Let's do that actually. Let's go to, let's see. Where is my, there it is. Yeah, let's do like this. Let's go to Mauser. So this one is 0.1 microfarad, 50 volts, that's correct. And it's 402, so that's correct too, which is good. So we can sort of mark this part as correct. Maybe I should actually go over all of the parts in turn and just mark them as correct. But I'll just start with this one for now. I'll add a field. Shall we call it like valid? Maybe valid. Yes. Let's make it 1. Easier to type. So when I next time when I go into this table of all the parts, I'm actually going to see the field, the fact that it's valid. Yeah. So this is just pasted from the table that they have in the in the KiCad where you're like supposed to assign footprints. So this is just in this table, and we should have the valid here. Do we have valid here? Actually, we don't, because we have to do like this. Let's do like this. So one of the things that I think is also quite annoying is if I do this, If I do this, I don't think it actually updates all of the sheets, which it should do, but it doesn't. So if I leave this, let's try to update here. Let's see here. So update fields from library. Value. Is it going to update all of the sheets? Let's see if we have some capacitors here. I think it's probably here. Where's the 100 nanofarads? Let's actually go here. I'm going to enter this sheet, and we're going to check this one. This is not updated. This is wrong. This is wrong. So this is like typical KiCad. You expect something to happen, and it doesn't happen because KiCad is completely stupid. You have to go into the sheet, and you have to do the update on every single sheet. You have to also remember to do that. So if you see here, now it's updated. Now it's not the auto part. Now it's the correct manufacturer number, and it's set to valid 1 there. So if we go like this, we can now see. We should be able to see the valid here. Yeah. So now we have the valid here, and this is the part that is a 100 nanofarad 50 volt capacitor. And there's still C13 left. Where did I leave C13? So look at C13. C13. Yeah, and C13, I actually replaced C13, but I didn't update the fields, which is the stupid way that KiCad works, that I have to update the fields on every single fucking sheet. So if I save this, now I can see that the 100 nanofarad 16 volt capacitors are completely gone, which is good. Okay, so we can go to the next one now. So let's go to the next one. Which one is the next one? Yeah. Next one is the 10 picofarad 50 volt capacitor. Picofarad 50 volt, 5%, 402, looks legit. I guess we could just say that this one is okay, at least as the part goes. As far as the part goes, this one is okay. 10 picofarad. So this one we can set to what the fuck? Oh, wait. 10 picofarad. Yeah, there we go. So I can set this to valid 1, and let's just check the parts themselves. So we're going to go to C4. Right. This is the loading capacitance. Now the thing is about the loading capacitance is we have to actually check this with the datasheet of the crystal. Let's take this crystal and let's look up the crystal. And I think this should be 12 picofarad actually. So let's have a look. So this is the crystal I'm going to be using. 10-1 UT, this one. So I can go here. Picofarad. And the thing about the loading capacitance is that you can actually adjust the loading capacitance to make sure that the crystal oscillates at exactly 8 megahertz. So this is something that's going to be dependent on the board. So depending on how you place the parts, how much stray capacitance you have in the traces, in the pins, the loading capacitance allows you to kind of adjust this precise resonance frequency of the crystal. So if you measure the actual frequency of the crystal, you can actually experiment with the loading capacitance and adjust it a little bit to make sure that it's that you actually get exactly 8 megahertz. And I think for this board, I'm going to keep it at 10 picofarad. And then we have this crystal as well. Let's have a look at this crystal. Oh, copied the wrong number. This one. Let's see. This crystal is the real-time clock crystal. Let's have a look what the loading capacitance is. Load capacitance, 7 picofarad, 9 picofarad. Let's see, 135. Yeah. Picofarad. Yeah, that's close enough. I mean, the only way to know exactly how much loading capacitance you need is to actually measure the frequency of the crystal when it's in the circuit, when it's actually oscillating in the circuit. So I'm going to leave this at 10 picofarads, and let's have a look at, I think there was only 4 of them, C4, 5, 6, and 7. Let's see, C4, 5, 6, and 7, yes. Next is 10 microfarad, 35 volts, 603. This one is microfarads, 35 volts. .603. Yep. Looking good. So we can actually set this to valid. Now, now we have to check that all of the places where I'm using this capacitor is actually correct place to use to use this capacitor. So I'm going to go and find C15 here. C15 is on the input to this regulator, and I think this regulator actually recommends 10 microfarad capacitor. Let's have a look. Yeah, we have C1 there, 10 microfarads. That's the standard recommendation. Obviously, you can also calculate the input capacitance. So look if they actually provide the formula. Choose 5R or 7R due to the low ESR. Personally, I don't like tantalum capacitors because I always solder them the wrong way and then they blow up. Let's see. Yeah, we don't need the 0.1 microfarad, the 100 nanofarad, sorry, because we're using the so we're using this one, and this one is X5R, which is legit. So C15 is okay. C18 then. What about C18? C18. C18 is 10 microfarads. I think I chose this one rather arbitrarily. Let's have a look. Let's have a look what the datasheet says. One microfarad. Okay. Input capacitor. It is recommended the amount of capacitance may be increased without limit. So because I'm already using the 10 microfarad capacitor, right at 35 volts, I might as well use the same capacitor. It doesn't really matter. It's just keeping my BOM low, which is good. Now, the output capacitor. Yeah, and that doesn't seem to matter either, so we can use the 10 microfarad capacitor there as well, which is only going to make things better. Okay, good. Now, 18 and 19. That's okay. Now we have the 22 microfarad capacitor, C17. Now, if we can replace this one with 10 microfarad capacitor, that would be good. But I don't think we can because this one is recommended to be at 22 microfarads. Okay, so this one is 802, 805, sorry. That's correct. 10 volts, X5R. That's correct as well. I set this one to valid. There's a huge benefit of using a library of components that you work on. I'm kind of trying to make sure that I can reuse every single part of a design. So I just have to design things once. And KiCad hasn't been very good at that by default, but it's still possible to make sure that you can like reuse parts. So 22805, that's, wait, what the fuck did I just do? See how KiCad makes it very hard for me to actually do things properly? Because I should have clicked that button there and set this one to valid. Because I should be changing the values in the library, not on the fucking schematic. And KiCad makes it possible to do this stuff on the schematic, which is wrong. There's actually one of the changes that I made in my version of KiCad, which I haven't ported to this latest, or this was the latest when I upgraded to it, but I haven't ported my changes to this one. And one of the changes that I made is that I disallow to change any kind of fields on the schematic, because I think it doesn't make any kind of sense. Let's see, which one was that? Was that like 10 microfarads? Was it this one? 603, yeah, I only have one of them. Yeah, that one is valid. That's good. Okay, so let's move to the next one. So we got C16. C16 is the one that is correct part. I think that this one is probably totally fine. I just need to pick the data sheet of this one. Okay, let's go here. Did I actually already have that? Yes, I did have that. Right here. Let's have a look at this bootstrapping capacitor. Where does it says that? Where does it say that it's supposed to be? Oh, yeah. So the datasheet says that the lowest value of this capacitor is supposed to be 22 nanofarads, which is sort of, you can use more. It's only better if you use more, because this capacitor is used just to switch the current in the inductor. I think there is a higher limit actually, because if you have too much capacitance, I think that I'm not exactly 100% sure what the effect would be, but I think it's actually detrimental to the regulator. Let's have a look here if they specify anything about this. And the bootstrap diode. Okay, they probably call it the output capacitor. Or no? No, this is actually C17 here. Where do they have the bootstrap capacitor? Am I blind? Can I not see where they describe the capacitor? They don't actually specify any information about this capacitor. Interesting. Well, as far as I know, using a 100 nanofarad capacitor works just fine there, and it usually does. But they don't actually specify any information any information about that capacitor, which is a bit strange. But that's the way it is. See if we can use anything else here. Okay, this is kind of a corner case. I'll leave it at 100 nanofarads because I don't think that it should matter, because the only thing that will happen here, it's not that many times bigger. The way I think, of course I could be wrong about this, but the way that I understand it, what is going to happen here is that it's just never going to be discharged fully. It will have more than enough capacitance to accommodate for each pulse that this regulator is switching. So that should be fine. C20 then. Yeah, C20 is part of that filter, which I'm going to leave at 100 nanofarads. C21. C21 is also that. Okay, D1, BAT54J, D1. That's fine. 600 milliamps is perfectly fine for this. And this will actually never be used because for the most part, this is only for sort of interfacing with this board or USB. And even though having wired this V-bus like this, it's actually going to be powering the board, which is fine in this case. I have this power switch here, so I prevent, in case something is connected here, but it doesn't have any power coming in, I prevent any kind of current flowing back through this regulator into the power lines, which is important in this case. But this should be fine. And it's SOD 123. Let's make sure that this one is SOD 123, and then we can just mark this one as valid as well. SOD 123. Good. Okay. Now, next one, D6. That's fine. D7. D7, I'm only placing D7 here because I have there is a possibility that I will have voltage flowing on the 3.3 volts, and this is because I have this debug connector here, which is supposed to power the chip when it's connected without any other power connected. But the problem is that it's actually going to be powering this regulator even when there is no voltage on the input of the regulator. So one easy way to solve the problem of reverse current through the regulator is to just place a diode there. So what I do is I just place a diode in reverse so that the thing is, like, it will only conduct when the voltage on the input is lower than the voltage on the output. And the only time when that will, or actually is lower than the voltage on the output minus the diode threshold voltage, which is around 0.2 volts here. So the only time when that will happen is if you have voltage here, but you have no voltage here, and you want to sort of prevent the damage to this regulator by pushing current backwards through it. And that's why you have a diode here, so that you kind of push the 3.3 volts here. And it doesn't really matter if the IOs are not powered when the debug connector is connected without any other power. But it's just important that the debug connector can power the chip so that it can program the chip when only this connector is connected. So this diode ensures that, let's say D7. Yeah, this diode ensures that this regulator doesn't get back powered. Then we have D2, that's the USB. I think this is the, yeah, this is the ESD protection for the USB. And it's connected with the positive V-bus here. That's good, and negative there. And then it has the 3 lines there, which is good. D4 is B240A. This is the regulator diode. This one is correct. And then we have the TVS diode, 5.5 volts. This one is placed on the 5.5 volts here. Yep. And now we have all the ferrite beads, FB1. Actually, let's go to B240. And I know for sure that this diode is correct, so because I've checked this one before. I'll just add a field here, valid 1. And let's check the ferrite beads. 603, which is correct. Yeah. Okay, that's good. So go to FB2. And the purpose of this ferrite bead is to filter any kind of switching noise that may be coming in from because of the signaling on this line, on the transmission line, and to filter it away from the to filter it from entering into the rest of the circuitry. Then we have FB3, and these ones are just for the buttons. Let's see. Okay. J1 is the USB micro. Yeah, and I used this one before, so I know it's correct. I'll just mark it as valid.
What's going on, guys? For today's video, I want to go over principles.
Yeah, fuck off. I'm just checking out some comments. Okay. Then we have this little jumper. There's going to be a little boot jumper. It doesn't have any footprint, so we have to pick a footprint for this jumper. Yeah, this one's nice. And once again, let's see. We should be doing it here. So this is found in the device library. Let's see. So what I do is I just copy this to my library, and then I assign the footprint in my library. What shall we call it? Yeah, that's correct. Now we have the coils, the common mode chokes. Let's see. Oh, by the way, I shouldn't forget to actually mark this one as valid. Yeah, this one I'll have to create. So I'm going to go to the data sheet, have a look at the footprint, and then just create the there we have it. Recommended landing pattern. I have some weird issues going on with my 3D rendering. No idea why it's not showing up. Nope. Yeah, that's better. And it doesn't seem to have any kind of standard footprint. So we'll just have to create one. So 0.6, 1.1. Let's move this one to 0.8. Let's duplicate this one. Okay, 0.8, and then 0.4 in between. Okay. I suppose according to the diagram, it's supposed to be like numbered like this. And of course, like the way I'm supposed to do this is like click, 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 double click. There we go. Let's also make the courtyard. I'm going to make the courtyard a little bit bigger, just to keep things a bit farther away from the inductor. There we go. Yep. Cool. All right. And then we can just set this one. Cool. Okay. That one is the same. We have L3. Oh, actually, the 3D model. Do they have the 3D model? No, they don't. I'm going to have to add some simple 3D model for this inductor. It's a pretty small inductor, though. It almost looks like a, like what could it be? Maybe 603. Just a little bit higher, though. Maybe 805. Yeah, it's more like an 805. Anyway. This one's 50-50. So yeah, I remember doing that one. So that one is correct. And I set the valid field on the schematic again instead of in the library. And it should be done in the library. So we have the L4. And this is the one that I'm going to be using. So like, once again, a different type of pinout. 1, 2, 3, 4. Let's make this footprint. So look at the data sheet. So 1.5 on Y and 2.25, I guess. Okay, my camera lost connection again here. I'm just gonna quit that window. So let's make this footprint. 5.5 in between there, so we can just do like this. Can move this one. I can just move it like edge aligned with the center there. I just press space, and I just move it 5.5 to this side. No, actually, not 5.5, but just half of that, obviously. And 2.54 in between there. Wait, what did I just do there? That was weird. So it's it's 2.54 from the middle, of course. Problem is we can't really know what the middle is. Let's try to guess the middle. So maybe like something like that. Yeah, most probably a little bit upwards. Let's move this one like that. So ideally I should be adjusting my grid into inches, but it doesn't really matter that much because it's such a small difference. Let's have a look here. So now it's supposed to be 5.5. Really? I messed up there. Yes, of course. That looks really long. That's 5.5. Oh. Put the courtyard around it. There we go. And the silk screen. It's not entirely straight. I'm going to fix it. And then we'll just renumber the pads. Okay, great. Now, time to update this one. And that's it for that one, for now. And then there is mounting holes, connectors, resistors, and a few other components left. So just continue with the review. All right, that's it for this video. And I'll just continue with the review, and then we'll see when I feel like doing another video. So thanks for watching, and do let me know in the comments what topics you find most interesting, and I'll see you later.